Right, well, it's a little past 10 o'clock here on the West Coast, so I'll go ahead and get started. Thank you all for attending this webinar today. My name is Mike Malakamati. I'm a bioinformatics scientist at the Banner Alzheimer's Institute in Phoenix, Arizona. I also am a research assistant professor at the University of Arizona College of Medicine in Phoenix in the Department of Biomedical Informatics. Very briefly, my research focuses on preclinical Alzheimer's disease, specifically with neuropathological and neuroimaging markers of preclinical Alzheimer's disease. But I am very statistically focused, and I serve as a statistician to colleagues outside of my institute and also within. And I also serve as a statistical reviewer for several journals, and that's sort of the going to be the theme of today's webinar of promoting statistical rigor in scientific manuscripts. So my hope today is to sort of give you my perspective of things that I've seen and continue to see as I review papers, in hopes that it helps people get a better understanding of what statistical reviewers are looking for in scientific manuscripts, and also to really help all of you have better papers and, have fewer reviewer comments when you're submitting them. So very briefly, just for the webinar itself, just be sure to mute your microphone during the presentation. Questions, you can submit them via the chat, or at the end of the presentation. I'm going to open it up to anybody who wants to ask questions live. I know that doing these Zoom meetings and webinars for the past almost year and a half, going on 2 years now, people may have some fatigue of not having that person-to-person interaction. So for anybody who wants to ask a question live, that will be available toward the end. But if you just want to submit the question via chat, I will address it at that time as well. The webinar today, excuse me, it will be recorded and it will be posted onto a YouTube channel that the Arizona Alzheimer's Disease Research Center Data Management and Statistics Core has. And I'll also be sending out that link to that YouTube page, along with the PDF version of the slides from today's presentation. So I have everybody's email address who registered for this webinar, and so I'll be sending those out to everyone who registered today. So just a couple of disclosures and disclaimers. So I have nothing to disclose in terms of financial interests or anything like that. What I do want to just point out and have everyone keep in mind is that the content that I'll be presenting today, it is not intended to be exhaustive, and it's just simply not feasible to cover the wide spectrum and the number of statistical issues that can arise in scientific manuscripts. The topics and ideas that I'm going to cover in this webinar today are based on my own experience, and I don't intend them to represent that of other statistical reviewers, generally. But I will say that these are based on some of the things I'll go over today are based on published papers about statistical reviews and just interactions I've had with other statisticians who do reviews. So some of that is based in part on those individuals, but really and truly everything you're seeing today in this presentation is of my own experience and opinion. So as I just briefly mentioned a little bit ago, the goals of this webinar are to provide investigators at all career stages with an overview of the common statistical problems and errors that are noted in the peer review process. And we also want to provide investigators with solutions and guidance to avoid these errors. So not just pointing out what the errors are and what we tend to see, but also really giving people the tools and knowledge they need to not make those errors anymore, and to basically increase the overall rigor of manuscripts that are submitted for publication. And more than anything, what I really want people to take away from this webinar is to get more knowledge and more confidence in reporting your own analyses in your own manuscripts that you're writing and submitting. So I'll start off by talking, about sort of the topics of rigor and reproducibility, which are very, very important and are still continue to get a lot of attention, in the scientific and medical fields. And as I think a lot of us know, there's a very large increase in the emphasis on rigor and reproducibility in peer-reviewed scientific articles. This is, very well known and, very prominent in the neuroscience area, where we, have, known for a long time now that, there's a reproducibility problem with several studies. And, the really what a big focus has been is that, the methodology and the analytic approaches, are really one of the central, areas that we can focus on in terms of increasing rigor and reproducibility. Over the years, there have been some efforts, to enhance the rigor and reproducibility that people are implementing. Many journals have reporting guidelines, and those have been helpful, but they don't really address a lot of the really, more granular and more specific issues with regard to how data are analyzed and reported. And the NIH in particular puts a very high emphasis on rigor and reproducibility. And I've taken this quote from their webpage, basically about what their view on rigor and reproducibility is in biomedical research. So when we start to talk about topics and things that have been noted in published research, when we talk, and specifically when we talk about statistical rigor, or in some cases a lack of statistical rigor, there are a few things that have been from published papers that have been reported, that really show that we have a long way to go in terms of getting investigators to really report their data and their findings in a way that is very transparent, but also be very reproducible. So the first one I just want to point out is that there's often a very low frequency of reporting of tests for the assumption of normality for outcome variables. So one paper that I took this finding from reports that about 21% of papers actually specifically state that they test for the assumption normality when they're using something like an ANOVA, a t-test, or linear regression. Another very concerning area is that a study that looked at papers in high impact journals found that many times these journals only report p-values for the primary analyses. And that can be a problem as well, since you're not seeing an effect size or any type of descriptive data with it. You're just given a p-value and told that it's significant or not significant. Now, although I mentioned that they're, from journals themselves have implemented guidelines, and, many journals themselves, do have very specific guidelines and things that they want, reported in the results sections of papers. But despite these, there's still, a very, lack of consistency in terms of reporting effect sizes for group differences and confidence intervals. So these are things that can be really helpful, to the interpretation of data, but we're still having a hard time of getting people to consistently, do these things across journals and across papers. And the fourth, thing that I've noted from, published papers that, I've seen on this topic is that there's actually, unfortunately, a very high rate of the incorrect usage of certain statistics and their interpretations in these published papers. So hopefully today I can help dispel some of this and really give people some solutions and some guidelines as to how to avoid these types of things in their own papers. So for me, in my experience as a statistical reviewer for journals, I tend to categorize or have found that most of the statistical errors that I see fall into one of these four categories. So the first one is that the incorrect statistical test has been used to address a research question. The next one, and probably this is, one that I see, most often, is that the incorrect interpretation of statistical tests, is being used. So, often people are, not interpreting a p-value correctly, or they're interpreting the p-value as a measure of effect size, and things like that. Another one is the incorrect use of statistical terminology, which is a topic I'll delve into later on in this presentation. And the fourth one is is one that, probably maybe most easy, probably one of the easier ones that can be addressed. And that's methodological approaches that prevent the optimal, analysis type from being used. So in many cases, the way that, investigators have designed a study, doesn't lend itself to being analyzed in a very optimal manner. So there are things that can be done to avoid that, and I will again touch on those as we go through this presentation. So generally, there are some very basic fundamental areas of concern for statistical reviewers. So generally, when a statistical reviewer is, reading through a paper and specifically going through the results section and, looking for, how things are reported and, where some errors may occur, these are, I've put these 5 bullet points down as sort of, really the big, the big things that we're looking for, right off the bat. As we go through the paper and read it in more detail, we'll often find, other small things that can be corrected or need to be corrected. But really, these are sort of the big things that we look for first. So the first one is, testing the assumption of normality for dependent variables when you're using parametric tests. So if you're using something like a t-test, ANOVA, linear regression, as we, a lot of us have learned, in our introductory stats class as an undergraduate, these tests assume that our data follow this nice, Gaussian bell curve. Now, there are, it is pretty well known now that these tests can be relatively robust to deviations from normality. So your data doesn't have to be perfectly normally distributed in order for these tests to work correctly and give you a valid result. What we often see, though, is that when we have, small sample sizes, or, if they're using an outcome variable that, has a history in other papers of being very highly skewed and not normally distributed, yet these tests are being used on it, that's going to raise, a flag, for the statistical reviewer. So that can be very easily addressed by doing a statistical test, for normality, which I'll go into in a little bit. The next point is unnecessarily dichotomizing or categorizing continuous variables. This one continues to be, a perpetual issue that we see a lot of, and we really encourage people not to do this, simply because you lose statistical power, by doing so. But there are also issues with how the data are interpreted if you're taking a continuous variable and then categorizing it or dichotomizing it at a arbitrary cut point. The next one is the interpretation or often misinterpretation of p-values. Then adjustment for multiple comparisons is something we're always looking for to make sure that that's been done. If you are reporting, several different comparisons, or lots and lots of correlations or things like that, we're looking to make sure that that those adjustments for multiple comparisons have been made. And lastly, the one thing that I put a lot of emphasis on and look for in the papers that I'm reviewing is to make sure that individuals are not equating statistical significance to clinical significance, because a small p-value doesn't necessarily equate to a clinically meaningful or scientifically meaningful effect or difference. So the first topic I'll go into in some detail, is testing the normality assumption. And so, as I mentioned, just in the previous slide, our very common tests like the ANOVA, t-test, linear regression, and Pearson correlation, they assume that our data follow this nice bell curve normal distribution. Now, if the dependent variable does not meet this assumption, it's very possible that these tests are going to be the results from those tests may not be valid. So what we can do in order to alleviate this problem is that we can actually perform a separate statistical test on our data to see if it actually does meet the assumption of normality. So some of the most common tests to do this are the Shapiro-Wilk, the Kolmogorov-Smirnov, and the D'Agostino-Pearson tests. So all three of these, perform relatively well in terms of helping someone determine whether their data do or do not follow the assumption of normality. And what's nice is that all of these tests provide a p-value that indicate whether the normality assumption is being met or not. Now, the way that we want to think about this and these normality tests is that higher p-values, so those that are larger than 0.05, these actually are ones that indicate that the data are consistent with a normal distribution. So for a normality test like the Shapiro-Wilk, if you get a p-value of say 0.23, that's actually good because it's indicating that your data are normal enough that you can use something like a t-test or an ANOVA. Now, if you get a p-value that's small, that's an indication that your data may not be normally distributed, and then you want to look a little bit more into that variable to look at its distribution and see how skewed it may actually be. So I've just put up this table here to show that there are some alternatives to the typical parametric tests that are so commonly used. So in this first column, I've just sort of listed out different some of the more common study designs that we see. So 2 groups, 3 or more groups, so on and so forth. In the middle column, these are the typical parametric tests that we use with them. And then on the right are some alternatives. So if you find that your data, are heavily skewed and you cannot use a parametric test, these are some non-parametric options, that can be used to still, analyze your data and still get a valid, and interpretable result. So the next thing I'll talk about, and I touched on this briefly, was the dichotomization or categorization of continuous variables. So a lot of times what I find is that, in the statistical analysis section and the results section, authors will say something to the effect of, well, our data were skewed, so we decided to dichotomize it at this point, in order to, avoid having to use a parametric test, and so that we could analyze them more easily. So there are some issues that, are, that go along with that, and actually, that's something that we prefer that people not do. And the main reason being is that you lose a great deal of statistical power when you turn a continuous variable into a categorical or dichotomized binary variable. Now, the main reason, another big reason why, statistical reviewers, why we really don't like people doing this is because very often, the cut point at which people have decided to dichotomize their data at are often arbitrary. So, I've seen authors where they dichotomize their data at the mean or the median or some other value. And then, the main thing there is that, the interpretation of that data, may not be very meaningful. So, if you dichotomize your data at a certain mean or median, the question of how that would apply to, a larger population is then, highly questionable. So really, we don't like to see data being dichotomized, just for these reasons I've stated above. Now, I will say that there are a few instances in where, dichotomizing a continuous variable is acceptable. And those are cases when, the cut point that is being used is, clinically or scientifically meaningful. So for example, if you are, categorizing people as being depressed or not depressed based on a standard validated, depression inventory, and that's okay because, usually in those cases, that questionnaire has been validated and to show, that yes, at this, score, these people tend to be, classified as depressed and those who are not depressed. And then, things like a cholesterol level, or, an HbA1c level, things that, if there's a very highly established cut point, that is very widely accepted, then it's okay to, dichotomize a continuous variable because then the interpretation that you have, has a lot of meaning in terms of its clinical and scientific relevance. The next topic I'll go into, and this is one that continues to be something that we see a lot of, unfortunately, is the interpretation of p-values in scientific studies. So the definition that I like to provide for what a p-value actually is simply the probability of getting a particular result, assuming that you have an equal set of conditions. And of course, we typically think of a significant p-value as being, less than 0.05, and then those that are not significant being greater than 0.05. So the thing that I want to really, underscore here is, that there are a few things that go into a p-value that, really, limit the way we can interpret, how much weight a p-value is given for a result. So there are three main components that really determine, what our p-value turns out to be for a given analysis. So the first one is the size of the difference between groups. The next one is the variability of the data for each group. And the third one, I have an asterisk by because this is really the biggest driver of p-values is sample size. So that's the really important thing you want to consider is that, very often, with small studies that, tend to be underpowered, you tend to not see a significant difference, because, the sample size isn't large enough to detect it. On the other hand, what we often see and hasn't gotten as much attention as it should is that studies that do actually have very large sample sizes, and are still, doing like a two-group comparison, and say they find a p-value of, 0.01, 0.001, for a variable, but, there's maybe, a 2 or 3 point, difference on that. So the example I like to give is say that there's a study of systolic blood pressure that was done. And we have one group whose systolic blood pressure is 123, and then another group whose systolic blood pressure was 120. So in a case where we had, say, 10 people in each group, it may be the case where we don't see a significant difference. Now, if we take those same systolic blood pressure values, 123 and 120, and now let's say that our group sizes are 250 and 250, then it becomes more likely that that 2-point difference in systolic blood pressure would be statistically significant. But we know that clinically, all of those individuals in both groups are still within a normal range on systolic blood pressure. So that's why it's really important to, and I really try to underscore the fact that statistical significance, does not necessarily equate to clinical significance. So when you're seeing p-values and interpreting them, it's really important to understand, what the actual, difference is, between two groups, if it's two groups on a continuous variable that, are being compared. So some of what I like to call fallacies of the p-value or, misinterpretations that are often, used. So very often, and I think probably the most common ones that statistical reviewers see is that people, interpret a p-value and they sort of interpret it in a way where it's a proxy of effect size. So indicating that a p-value, is representative of a large effect, which is not the case. The next one, which, we often see is that, people interpreting a p-value of above 0.05 as saying there is no effect. So that's not necessarily the case. Oftentimes there may actually be an effect or difference that is present, and it just wasn't detectable, given the sample size or some kind of bias in the data. And then the third one is probably I know this is a very common interpretation, but it's still not one that I prefer to see, and I'll explain why. So when I see the interpretation of, the p-value is the probability that the results are due to chance alone, I don't like that, because when a study, yields results that are not statistically significant, we're not just going to say, oh, it was due to chance that we didn't see, an effect. There are a lot of factors that go into, why we may not have seen a significant difference. So, things like, something about the sample that we're using, is different from what other studies have shown. Or, there was some kind of bias or measurement error, lots of things other than chance, affect whether or not we're going to see, a significant p-value or not. So, I just want to caution people in how you interpret your p-value in your papers, to really shy away from, doing these kinds of things, and really, take some emphasis off the p-value in terms of, what weight you're giving it in your text, and really focus a lot more on, the effect size or the difference that you're seeing, between your groups. And I like to add this slide in just to really hit home the point. I like it because, it's basically saying the scientist is saying your p-value is greater than 0.05, and your chance of drowning is not significant, yet here the guy is drowning. So again, just to really reiterate the point that, p-values, should not be relied upon to, make decisions about, the clinical or scientific importance, of a difference or an effect. So it can be helpful in determining, but really we need, it's better to not rely on it solely to make that decision with. So then, related to p-values, aside from their interpretation, there are actually several reporting errors that we often see with p-values. And one of the most common ones is where we see investigators report p-values which are essentially zero, which, intuitively, you cannot actually have a p-value of zero. So I know that the reason why this often occurs is because there are several statistical programs that basically they don't report decimals past a certain point. So if your p-value is very, very small, very often you'll get a program that gives you just, p equals 0.0000, and it leaves it at that. So what I recommend is that, and I really advise people not to report a p-value like you're seeing in this first bullet point, but use, what's a very common way is to report it as p, less than or equal to 0.001. And so if you have a statistical program that, gives an output where the p-value is essentially, zero, it's better just to, in your paper, report, p less than 0.001. And you can also apply this rule, when p-values from statistical output are also very small. So if you do have, a more advanced or more, more technical program that actually does report exact p-values out to several decimal places, you can still use this p less than 0.001, to note that in your paper. The next topic I'll talk about is multiple comparison adjustment. So I think this is probably something that, most people are at least somewhat familiar with, but I've put, this, slide in here to really show, when we talk about alpha inflation, and when we're talking about, having, several different statistical tests that we're making comparisons on, if we're making all of those comparisons at the 0.05 level, that increases, the probability that we're going to have, a type 1 error. And in order to, decrease that and maintain our 0.05 significance level across all of those tests, is that we have to adjust our significance level in order to do that. So the most common approach is the Bonferroni method. And this is simply taking the significance level of 0.05 and dividing by the number of comparisons that are being done. So for example, in a say a study that has 6 comparisons, that would give us a new significance level, or a Bonferroni adjusted significance level of 0.008. So based on that, the p-values from our different comparisons would need to be equal to or lower than 0.008 in order to be statistically significant, and still maintain that appropriate level of type 1 error correction. Another method that is becoming more popular is the false discovery rate. And this one a lot of people are starting to use more, and I will say I personally use this in the statistical work that I do with my collaborators, in that the FDR method is not as conservative as the Bonferroni method. And the nice thing about the false discovery rate method is that it accounts for the number of p-values that you're comparing, but also the p-values themselves. So if you have where the Bonferroni method just simply ignores what the p-values are in your comparisons, the FDR method actually takes that into account. And if you come across papers in GWAS or a lot of neuroimaging studies where we do a lot of voxel-wise analyses, the FDR is used I would say almost more than 90% of the time in these cases to correct for multiple comparisons. And then, lastly, I'll touch on statistical versus clinical significance. And in recent years, and this is becoming more prevalent now, is that there's been a lot of criticism on studies that rely solely on p-values in order to, make interpretations and decisions upon, what factors are, significant and not significant in terms of, disease risk and other outcomes. So one example that I always find very striking is that the over-reliance on p-values basically led to the identification of over 300 risk factors for heart disease, and this was in 1986. So I like to bring this one up because really from a practical standpoint, when I use this slide and talks to clinicians, is that there's no way that a clinician can address this many risk factors, reasonably for their patients. So that's really kind of my, favorite way to argue and to show that statistical significance does not equate to clinical significance. So the way that we can get around this and really, start to address and, provide some, measure of clinical significance is by using effect size measures. So I want to point out that effect size is an umbrella term. It's a very general term because there are many different types of effect size measures depending on the data that you're looking at and using. The example I'm going to give here is if you had 2 groups that you're comparing on a continuous variable. So I'm just using this, this one because it's a very common, type of analysis, and it's very easy to sort of demonstrate effect size using this, but just know that there are several different measures of effect size aside from the one I'm going to show here. But why it's important and why it's helpful is because effect sizes give us a much more meaningful interpretation beyond just a p-value that tells us significant or not significant. And really the effect size measure really allows us to say if there's a meaningful difference between the groups that we're comparing. And just very generically, when we talk about an effect size measure for, on a continuous variable for 2 groups, we're basically taking the difference of their estimates, usually means, and then dividing by variability, such as a pooled standard deviation or something like that. And so so what I'm showing here is the Cohen's d effect size. And so this is the most common one that is used when we're comparing 2 groups on a continuous variable. And in the Cohen's d and other similar types of effect size measures, you can use a pooled standard deviation that takes the standard deviation from both groups, or you can simply use the standard deviation of the reference group. And then here, this guideline is how, these effect sizes can be interpreted. And my convention and, my approach is that usually anything that's a medium or a large effect is something that is clinically meaningful. So, small effects by themselves can still, be somewhat relevant, given, a particular context, but really, when you're trying to interpret something, to be clinically meaningful, my opinion has always been, and it's got to be at least fall into this range of a medium effect up to a large effect. In addition to effect sizes, confidence intervals are also gaining a lot more traction and a lot more popularity in terms of how we report statistics and report our data in papers. So the confidence intervals, they also take another step above the effect size, and they provide us with a measure of accuracy or precision of our estimate. And really and the nice thing about confidence intervals is that they can be calculated for a number of different measures or metrics. So you can get a confidence interval for a mean, percentage, difference of means, really, anything. So this is what makes it nice. And just from a practical standpoint, it gives readers a really clear way to show what your margin of error or variability is for your data. And what confidence intervals also do is it takes us away from this sort of binary significant, non-significant interpretation of results, and it allows us to take a more estimation-based approach to interpretation. And really, this is where a lot of journals are trying to sway people to go. And there are lots of articles and books that are actually starting to emphasize this estimation-based approach to statistics now, using effect sizes and confidence intervals, where we can we're not saying that we have this very precise estimate, but we're saying here's a range of estimates that we think are reasonable, given our data. And then, of course, with confidence intervals themselves, when we have the lower and upper bounds for them around our estimate, we typically want those confidence intervals to be, relatively close to our estimate, because this indicates a high level of precision or accuracy. And then, of course, when our confidence intervals are wide, or when they start to become farther apart from our estimate, this is telling us that there's more variability and less precision, with the data that we're reporting. Right. So as far as calculating confidence intervals go, most of the time, our go-to statistical programs do a good job of giving these in the outputs, but they're basically usually using a very standard parametric approach where you have the estimate, then it's plus or minus 1.96 times the standard error. So that's the very general and most common way that confidence intervals are calculated. But another very an approach that's becoming more popular is what's called bootstrapping. And what this involves is basically deriving several sets of confidence intervals from multiple iterations, from resampling the data set. And what's nice is that this bootstrapping approach doesn't rely as heavily, on the distributional assumptions that that standard parametric approach it has. And what this may do is it may reduce some of the bias associated with the more traditional approaches to confidence intervals. So I bring this up just as a viable alternative to calculating confidence intervals. But more generally, I will say that if you're unable to do bootstrapping and you just have the regular basic confidence intervals from your statistical output, I will always say that some confidence intervals are better than no confidence intervals. So even if you're just reporting the ones from your output, that will please a statistical reviewer much more than not having confidence intervals. All right, so for this next section, I'm going to talk about some very specific statistical reporting errors that I often see in the papers that I review, but I'm also going to give some points and some advice on how to avoid them or to correct them. So the first one is when in studies that use logistic regression, so this is when you have a dichotomous yes or no, disease yes, disease no, case control, this is when that's the dependent variable of the study. And the most common error I see, unfortunately, is with investigators who are using SPSS. So I don't say this to knock SPSS in any way, but what I want to caution those of you who use it about, especially in logistic regression, is that unfortunately its default output is to give you a regression coefficient or beta and its standard error. Now, the thing with logistic regression is that we want an odds ratio with its confidence interval, because again our main outcome of interest is the odds of being in either a control or or a case group based on a predictor variable. So instead, what I really encourage individuals to do, there's an exponentiated beta, where you're seeing the exp with b in parentheses, and it's 95% confidence interval that can be retrieved in SPSS when you're doing logistic regression. And this is what you want to report in your paper, because what this is the exponentiated beta is the odds ratio and it's 95% confidence interval. So if you're using logistic regression, this is what you want to be reporting. And I want to emphasize this case only applies to logistic regression. So if you're using another type of like linear regression or anything like that, still just report the betas and their relevant statistics and don't exponentiate them. This is a special case for logistic regression. So the the next thing that I see quite a bit of is terminology and application of certain things in papers that could be done differently to better express the data, but also terms that are not used properly. So the first one I'll go through is the argument between using standard deviation and standard error as the measure of variability for your data. So one of the most common things that I see, and often people don't, some people don't see this as an error, but in the context of what is trying to be expressed in the paper by an investigator, this is a very important point to consider. So it's very common, and I know that those of us who have colleagues and work in more of the with animal models and with more of the bench science, is that it's very common to report standard error for their estimates. And I understand why some of them do, but really in what the standard error is not really giving you a true estimate of the variability for that sample. So what the standard error is basically an estimate of precision when you're comparing a sample to a population. So you have to balance that with what standard deviation actually is, which is an estimate of variability for a population from which the sample is drawn. So the standard deviation is specific to the sample, whereas the standard error is basically extrapolating and giving you a level of precision with regard to a population. Now, the standard deviation, I will say, is a more commonly accepted measure of variability when the mean is being reported. But there are some cases where a statistic doesn't lend itself to having a standard deviation, such as a regression coefficient. So with a regression coefficient, there it's reasonable to report standard error of it, so that you're getting that measure of variability with it. With regression coefficients too, you can also report a 95% confidence interval, and that serves just as well to characterize the variability of that estimate. But in terms of reporting means, the standard error is always going to be, sometimes substantially smaller than the standard deviation. And, in doing that, you may not be accurately reflecting the true variability of the data. So if you look at how, what standard error is, it's standard deviation divided by the square root of the sample size. So if you have a relatively good sample size, your standard error is always going to be, relatively low. And so when you're reporting that, it can be a little bit misleading because it's not really telling you, what the nature of the variability is for your sample. And I'm going to highlight that here in this example. So what I'm showing you here are two bar graphs of the same data. We're looking at differences in females and males on the AVLT total learning score. On the left, you're seeing them, compared on their means, and the error bars represent standard deviation. And then on this similar graph to the right, these error bars represent standard error. So you can see very clearly that, these error bars are quite different, from these graphs. And, for me as a statistical reviewer, I want to see, the standard deviation in this case, as opposed to the standard error, because this graph on the left is more informative, and it's actually giving me a better idea of what the variability in those groups is looking like. Right. The next, topic that I see a lot of is the erroneous use of multivariate and multivariable, in papers. So the term multivariate refers to analyses that have multiple dependent variables that are being analyzed simultaneously. And multivariable, these are analyses where you have multiple independent variables that are being used to predict a single dependent variable. And I want to emphasize that these two terms are not interchangeable. And most of the time, what is being reported in a paper is a multivariable analysis. So something like where you have, a mini mental status exam score as the dependent variable, and then you have some demographic predictor variables, or others as well. So in this case, what we're looking at is a multivariable analysis and not multivariate. So, if a really good way to avoid a comment that you'll have to make a correction on is to be sure that you're using these two terms correctly. And again, most of the time, it's a multivariable analysis that's being described. The next one that I often have to help authors through is the difference between mediation and moderation. So I will say that just generally, it's really common for those who are not statistically inclined, but who kind of understand basically the concepts of mediation and moderation to sort of use them interchangeably. But really, mediation and moderation are two very different concepts that are used to talk about how variables outside of our predictor and dependent variable are affecting our analysis. So mediation implies that a variable is in the causal pathway between our X and Y variable, or our predictor and dependent variable. Moderation refers to how a variable M indirectly influences the relationship between X and Y. So the term moderation is not used that often. And really we tend to think of mediation a little more because it's a little bit more conceptually clear. But just from a statistical standpoint, we want to be very clear about whether the data we're reporting are from a mediation analysis or reporting a moderating effect. So these two figures here I really like, and I've put the reference here at the bottom left if you want to go find the paper. These are a great way to visually characterize the difference between mediation and moderation. So here up in the top with mediation, here we see that the variable M is in the causal pathway between X and Y. Now down here for moderation, we see that this variable W is simply, acting on this, direct relationship between X and Y. So conceptually, this is the difference between mediation and moderation. Now, from a statistical standpoint, moderation basically is derived from regression models that have an interaction term. So if you're including an interaction term and reporting that as your effect of interest, you want to basically be very clear that you are reporting a moderating effect of a variable on a predictor and not a mediating effect. Right, and I'll show an example of this in a very simple regression model. So for this model, what we're simply asking is does phlerbeta-pure SUVR or amyloid load measured by PET scans, does that moderate the association between ischemic risk and white matter hyperintensity volume? So white matter hyperintensity volume is our dependent variable, with vascular risk being our independent variable of interest. So in this model here, we have both the main effects of vascular risk through the Hitchinski score and our main effect of amyloid SUVR. And then on the third line is the interaction or the moderating effect of the amyloid SUVR on the Hitchinski score or the vascular risk. And in this case, the p-value is not significant. So we can interpret that as being that, there is no, the association between vascular risk and white matter hyperintensity volume is not moderated by amyloid SUVR. So again, when we talk about an interaction term, especially an interaction term from a regression model like this is how we define and measure moderating effects. So I won't go into how to do a mediation analysis, but what I will say is that the assumption is, again, that this third extraneous variable is somehow in your causal model, or in the causal pathway between your predictor and outcome variables. And there are more specific statistical tests that are used to do mediation analyses. I won't go into those, just, it's a little bit out of the scope for this talk, but those are relatively easy to find and easy to do once you see them. The last topic I'll cover is covariate selection for regression models. So very often, if we're running a regression model, usually, our basic, linear regression model, it's very common that we want to have covariates in order to adjust for their effect on the dependent variable, things such as age, sex, and education. Those are the main ones that we typically see in aging and Alzheimer's disease. Now, what I want to emphasize in these next few slides is that your selection of covariates, should be and is typically based on, established biological, and clinical relationships with a dependent variable. But there are also other factors to consider when you're selecting covariates for your model. So the first thing to consider is multicollinearity. And this is when you have covariates in the model that are highly correlated to each other, and they end up reducing the precision, of your other estimates, particularly the ones for your variable of interest. So when you're selecting covariates for your model, you just want to, ensure that, you're not selecting a lot of them that are highly correlated to each other. The next topic, and this is something that is used quite a bit by individuals, is these automated selection procedures. So forward and backward selection in building models, with and without variables. So these automated stepwise selection procedures that a lot of statistical programs use, they're including and excluding variables based on their p-values. So the problem with that is that you may end up excluding ones that are still biologically and clinically relevant, for the relationship that you're looking at. The last part is one that is not covered as much, but is still relevant, is that there are often big debates about how many subjects per covariate you have to have in order for your model to be valid. So, very often a criticism that you might see from a statistical reviewer is that if you have a regression model that has several different predictor variables in it or covariates, and your sample size is not necessarily large, maybe 20, 30, or 40, you may get a comment saying, do the investigators have a large enough sample size to use a regression model with this many covariates? And there's been this rule of thumb that people have adopted over the last couple of decades that you have to have 10 subjects per covariate in your model. This is a little bit erroneous because this is actually came from a an epidemiological study where they were basically saying that you had to have 10 covariates when you're assessing the risk of certain outcomes with logistic regression models and things like that. Unfortunately, that was has been taken and applied to other kinds of regression models where not necessarily the case. So really, your covariate, the covariates you select to be in your model, should be study dependent, and don't rely strictly on one rule that basically is telling you that yes or no, you cannot include these covariates because of your sample size. So again, you want to avoid overfitting your model with lots of covariates, but again, you don't want to limit yourself in adjusting for things that are really important if you don't have a very large sample size. So here are basically some recommendations I have that I give to people when really kind of fitting the regression models. And so the very first thing is you want to select your covariates based on their biological and clinical significance. So right out the door, that's what you want to do, because me as a statistical reviewer, when I'm looking at somebody's regression model, I'm always looking to see, did they adjust for this, 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 and this? So if you have those, if people have been diligent and have put in the things that are known to be biologically and clinically relevant, I'm not going to make a comment about that, and I will basically say, yes, this model was built appropriately. And I would avoid the use of automated selection procedures. And again, because even though a variable may not show a significant p-value in the model, it may still be very highly relevant in the field. So for example, adjusting for sex, even if there are no differences in sex on your dependent variable, you're still there's still reason enough to include it in the model because it is so highly associated with differences on many dependent variables. And again, really consider whether your covariates are highly correlated and whether you can take one or two out because the variance is accounted for by one covariate that's highly related to those others. And again, as I mentioned before, don't overfit your model with too many covariates. There are a lot of reasons for this, but mainly, so that you're not, taking away, overly taking away from some of the variance that your variables of interest might have, but also so that you have a model that's easy to interpret and easy to apply across different settings. Now the model fit, or determining whether your model is good or not, you can use adjusted R-squared values or the Akaiki's information criteria, or AIC value, to do that with. So if you're sort of going back and forth and taking out and entering variables into a model to assess its fit, you can use the adjusted R-squared or the AIC value to determine whether you're getting a better model fit with or without certain covariates. So to sort of start to conclude is that increased statistical rigor is going to promote reproducibility. So as you're going and writing your papers, try and keep these things in mind. Is that be sure that you're describing in detail all of the analyses that you did in a statistical analysis subsection of the method section. The most common practice nowadays is that in the methods section, you have one subsection at the end, right before the results, that is your statistical analysis section, and you're detailing, all of the analyses you did, and which tests were used, what the significance level was, and things like that. In addition to that, be sure to state which statistical software was used for the analysis. So you want to include the software name, the company name, the version, and the publisher. For those that use the program R, which I do quite a bit, you want to not only state and cite that you used R and which version, but you also want to list out which packages in R were used for the analysis. And when possible, do report all the descriptive statistics for your independent variables, and as well as for dependent variables. And this is especially important for group differences on continuous variables, because this allows for more transparency and for other readers, to really get a better feel for what your data look like. And this also makes the job of statistical reviewers a little bit easier. Another reason why it's good to report your descriptive data is because it helps others do meta-analyses. So I know that for a lot of times when we're when a lot of us are writing papers and putting together a results section, we're not thinking about, well, what if somebody wanted to do a meta-analysis using this study? But that's actually a really good thing to keep in mind and think about as you're writing your paper, is that thinking, well, if somebody wanted to do a meta-analysis of this, could they do it? Or do they have the mean and standard deviation and the sample size for these continuous data? I say that because very recently I've been working with a couple of students on meta-analyses, and one thing that we've run into is we've had to exclude studies from the analysis because they simply didn't report the descriptive data in any tables or anything. In some cases, they reported, we had to go find the supplemental material on the journal's website, and we're able to get the data that way. But in some cases, the study just couldn't be included simply because we didn't have the raw data, or not the raw data, but simply the descriptive data available to us. So what I really want to emphasize and be the take-home messages for this is that we really want to first, in our analyses, if we're using continuous variables as our dependent variables, be sure that we're doing and reporting tests for normality to make sure that they are meeting the assumptions of the test we want to use, and if they're not, do we use our non-parametric alternatives. Standard deviation is a more accurate measure of group variability than standard error. So for those who are, I guess, more practiced in reporting standard error, I would encourage you to go and try to report standard deviation more, because that's going to give a better reflection of the variability of your data. When possible, please report effect sizes for group differences on continuous variables, and also confidence intervals as well. Those two things will be really, really helpful, and will help make your data much more clear when it's being reviewed. And again, when you're building regression models, your covariate selection is very important and should be based primarily on scientific and clinical rationale. So with that, I will leave you with some references that go into some of the topics I've done in more detail. They're also interesting to read, if there are specific things that I didn't get into as much. And again, I'll make these slides available to everybody. I will email them to all those who registered, so they'll be coming to you later today or next week. And with that, I just want to say thank you very much for attending this. The Data Management and Statistics Core of the Arizona Alzheimer's Disease Research Center, we are aiming to do more of these. Our goal is to do these somewhat quarterly, but we don't know if we'll be able to do these regularly or not, but we do anticipate inviting other individuals both within Arizona and outside of Arizona to give these types of webinars. So with that, I will go ahead and begin the question and answer session. And I think I have one question in the chat here. No, it was just a comment. Okay. All right, so if there is anybody who wants to ask a question or bring up a topic or something they've encountered, I'm happy to do it live with you, or you can simply enter it into the chat and I will gladly answer it for you. And if you have a question, you can just, if you want to just, either raise your hand or just unmute your mic and start talking. So yes, Natalie, go ahead. You can unmute yourself.
Hi, Michael. Thank you so much. This was very helpful. I'm a graduate student and you're working on several manuscripts. So this is all very prescient and very prudent.
Excellent.
Quick question.
Yeah.
So when you report that last point, one of the last points you brought up, reporting kind of at the end of your methods section, all the analyses that you had laid out. What do you do in the case, you set out to have a certain question answered, and as you're doing, you set up your analyses, of course, ahead of time, but as you're going through the data, you uncover other questions that you didn't initially plan to address, but have sort of come up. Do you still add those into the section, or does that like ruin the surprise, if that makes any sense?
No,
the discovery.
It's a great question. I will say that I often grapple with that with myself. So, you have the, so often we have sort of these post hoc analyses that we do as, certain things come up with the results. So what I sometimes do is, if the post hoc analyses get to be very complicated, I will put those, in that statistical analysis section. If it's a fairly easy, and straightforward post hoc analysis, I'll just say, in the results section where I'm reporting that result, I'll say, we then wanted to explore the effect of such and such, and then here's the result of that. So my answer to that is it depends on the complexity of the post hoc analysis that you're doing.
Got it. Thank you so much.
You're welcome. Javad, go ahead.
Hi, Mike. Thanks for the brilliant talk. It was very interesting. I had a question. Maybe it's a little bit off the topic. If it is, let me know and we will discuss it later. But the question is, when you're doing statistical modeling and you have identified a couple of parameters that, for example, you think has impact on the outcome, and then you are building the model yourself, so you're not using the traditional models or the test, then how do the statisticians go with deciding that, okay, if should we go, for example, A plus B multiplied to D, or if we have these parameters? Is there any way to decide on that, or is it just more of a trial and error approach?
So one of the things that I talked about, and it's in the slides, is you can use either the adjusted R-squared value or the AIC value. So for a basic linear regression model, often what we do is that we will start off with a couple of variables, then add more, and we will see how much that R-squared value changes. So if we see it go up substantially as we're adding variables, then that's telling us that the model is, we're getting a better model, and we're accounting for more of the variance in our dependent variable. Now the AIC value, or the Akaike's information criteria, that's a similar one, and it's somewhat less informative because it doesn't give you the percent of variance accounted for in a model. But what it does is, if you have several models that you're trying to test or compare, it's a really good way to see how they stack up against each other. And with the AIC value, what you're looking for is a lower value that indicates a better fit. Now, the thing with the AIC value is that in this, this is a question that I think is, I have yet to see a formal guideline or paper that looks at this, is that there's no established cutoff or value that says, yes, if your AIC value changes by X, then you have a better model. I've seen one, just very random sort of rule of thumb that I found due to doing a Google search. I think it was on some lecture slides from a professor somewhere that said, yeah, a change of 6 in the AIC value, indicates a significantly better model fit. But again, I've not seen anything published or standard to say, yes, here's when your AIC changes by this much, here's this is a better model. But those are the two metrics. The adjusted R squared and the AIC can be used to determine which variables should and should not be included.
So just a quick follow-up. So both of them, I mean, I'm familiar with R2, but not the other one, but I assume both of them need some kind of a ground truth data so that you compare, right? So you have the model, your model gives some result, you need to have a ground truth that you compare them, you get some error or residues, and then you calculate such stuff. So in case of, for example, when there is no true labels or true data, is there any method, for example, I mean, if you are familiar with, unsupervised learning, they have came up with some ideas of how to do that when there is no labels, but in a statistical modeling, if there is no true data or label, is there any methods for checking how good is the model?
Yeah, so one approach that I take is, I will start off with what I call a reference model. And that's, just has the basic, bare, sort of essentials. And then after that, is when I start to add other things to see if they're, to see how much they're changing the adjusted R squared or the AIC value. So, so to answer your question sort of about, this grand truth, if you will, is that, I will say it's not really a grand truth. You're basically just, I'm starting out with a reference that, I consider to be a starting point and then going from there.
Okay, that works. Thanks a lot.
You're welcome. Anybody else, feel free. I know that, we don't, there's enough of us where, we can, have, the direct conversations as opposed to just doing chat stuff. But yeah, I allotted quite a bit of time for this, so that people could ask questions and, we can have discussions on this. I anticipated people, having, experiences of a review for a manuscript where, they weren't sure why the reviewer, said what they said or how they could address it. So I'm very happy to talk about those if you have those kinds of examples.
Hi, my name's Philip. Thanks so much for your presentation today.
You're welcome.
One question I had and just wanted your advice or experiences on is whether or not to include p-values in a table 1 like descriptive, a descriptive table, because I've gotten, at least in my limited experience, gotten kind of both sides where some journals want p-values, but then some of the biostatisticians I work with, don't like the idea of reporting p-values for, just descriptive results.
Yeah. I will say that I've been through the same thing. So I will say that, one of my collaborators, it's a group of collaborators that I have where, they, have for years regularly reported, p-values in their demographic and, descriptive tables. And, they, their mindset is, and I, to a certain extent, I agree with this, is that if you do that, then you're sort of, preventing, a reviewer from saying, oh, why aren't there p-values in your table 1? In that same regard, I think that, there have been times where I have, submitted a paper with a table 1 with no p-values, for the group differences. And, I've had, the reviewers haven't had an issue with it, or, no one's really said anything. So my thinking is, I think it depends on the type of journal you're sending it to. If you're sending it to a more clinically oriented journal, you can probably not report the p-values in table 1 because people are just more interested in the descriptive data. And that's really what kind of clinicians are more, oriented toward. If it's a more, scientifically focused journal, say something like, Cortex, Brain, Journal of Neuroscience, then you're more likely to have a reviewer who wants to see the p-values in table 1. So you could just sort of adopt as a rule of practice to go ahead and do the p-values for your table 1 and just make sure, because that's going to, it's going to appease, the reviewers who want it in there. And then, for the reviewers who could care less, they're not going to say anything and all that. So that may be one approach you could take.
I see. Yeah, thank you. That's helpful. It's helpful to maybe think about it in terms of the audience for
Yeah.
the journal. So
Mhm.
Thank you.
Yeah, you're welcome. So just out of curiosity, did you all find the information here informative and helpful? Like, is it going to, kind of change the way you approach writing and when you're reporting your data? Ah, good. Good to hear. Are there, and just out of curiosity, are there any topics, specific topics that you would want to see in this sort of webinar series? These are going to be geared more towards, methodology and statistics. So are there certain things that, you guys would like to get a more in-depth, or see a more in-depth webinar on?
I'll just chime in.
Yeah.
I have encountered some issues in multiple comparisons testing. I do a lot of correlation analyses in functional MRI.
Mhm.
So, even I rely mostly on FDR, but sometimes it's been, I want to avoid being overly conservative when there's some maybe shared variance in like networks, for
Mhm.
instance, testing networks. So I'd love if other folks would be interested in that too, some more in-depth on alternative multiple comparison corrections for sort of highly correlated comparisons.
Okay, excellent. Thank you.
So something that would be of my interest would be on sensitivity analysis and parameter sweeping and techniques that I don't know if that's really related to what you have in mind, but on a statistical point of view, that is something I'm working on. So if it's related to the whole clinical type of research, that could be interesting.
Okay. All right. Well, if there are no more questions, thank you all very much for attending this webinar today. As I mentioned, the link I'll send out the link for this once I get this posted to our YouTube channel. And I'll also, in the email, I will also include a PDF version of the slides from the webinar today. So thank you all very much. Have a wonderful rest of your Friday and enjoy your weekends.
Thank you very much.
Welcome.
Thanks a lot. Same to you, Mike.
You're welcome.